I'm Bhavidhir V. Bharadwaj. Welcome to episode 17 of Genesis of Tomorrow. The following is a conversation about quantum mechanics, mathematical approaches, and much more with Dr. Rahul K. Balaji, a researcher at Princeton University and doing his PhD in theoretical and mathematical physics. Also, 86.1% of you watching this have not subscribed yet. If you get even the slightest bit of value from our show, please support us by clicking that subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. It's begun. Okay. Let's start by briefly talking about the state of quantum mechanics. How far have we really come from the 20th century in terms of theory, but as well as experiment?
Right. I guess there are a couple of different ways to answer this. So with the theory side of things, mm, uh, a lot had been done already within the 20th century in terms of laying the foundations for the theory that we use today. But where we've gotten ahead is some of the technology that we use, mathematical and in terms of our compute. Um, the mathematics of things primarily deals with how we try to solve more complicated systems or complex systems uh, with um, many body interactions and so on. And I feel like more on the application front, that's where we've gotten ahead, um, especially when we talk about quantum computing, etc. And that ties into the experimental stuff we've gotten ahead with ion traps and so on being recently designed in the 21st century. Um, so yeah, I would say that's roughly where we are at right now compared to the 20th century. But yeah, at any point, feel free to stop me and yeah, I can explain more about these things and so on. Yeah.
I would love for you to probably take a deeper dive towards the mathematical formalities and foundations of it, like from Hilbert spaces and operators and the wave function, all those things. Like for complete
Right.
novice, maybe listening to this
Right.
conversation,
Yeah.
how would you explain all these relatively complex mathematical theoretical stuff?
Right. I'll be happy to. For that, maybe we can go back to let's say the 1920s, since that's where it all started. So yeah, back then you had some hints for um, wave-like behavior of particles, right? So at very small scales, um, primarily. So people started wondering if you can formulate the dynamics of the particles as waves. So we knew how to deal with waves from electromagnetism. So we started off with the math that's available from there. Schrodinger was one of the people who were like, fine, why don't we take the ansatz of a wave and see where it leads us? Um, and what he got back was, yeah, this wave formalism. But the wave formalism that doesn't happen in real space, but in a sort of complex space because of the presence of the I, which is root of -1. Um, so there were certain properties of the space where you can take projections along different basis vectors that give you different components of what makes up your wave, essentially. And yeah, because of other properties that it followed, we gave it a name called the Hilbert space. Um, Now, this might be very weird to think about because all this physics is happening in some space that's actually not real. That's purely mathematical, one might say. But its effects are evident when you get into real space. For example, the square of the amplitude or the square of the wave, essentially, gives you the probability distribution for the particle existing in real space. So this was the first departure from what we are comfortable with describing things in real space. But if you put it in retrospect, like all of physics, this was a step in the direction of abstraction. It's no different than the other steps that we have taken. Um, but yeah, so that's where it all started, and there, this Hilbert space is essentially a space where vectors live. Vectors are things with magnitude and direction, right? And you can actually multiply matrices with these vectors to transform them. And these matrices that acted on vectors in the Hilbert space are called operators. So everything that we had to do in quantum mechanics had to do with these operators and their properties and so on. Fast forward to the advent of quantum field theory, where um, we didn't really consider special relativistic effects when we started working on quantum mechanics. That is, we considered time to be some clock that's running and non-dynamic, and so on. But with the advent of special relativity, we know that time can slow down or speed up depending on your motion and the space around you and so on. So they tried incorporating this, and quantum field theory was born. Um, it's not completely solved yet. That would be left to a field called quantum gravity. That is what I work on. But we can talk about that later. But so some of the tools here sort of bolstered quantum mechanics and made it a little more abstract, where you have fields like topology in differential geometry and all of these fields coming into play to help explain the nature of these operators in different settings. And yeah, that leads us into the early part of 21st century, where you had things called topological insulators and very niche materials that help make our lives so much better with their unique properties. And all of these being explained by seemingly very, very abstract math. So yeah, that's a rough overview. Yeah, we can dive into a lot of tangents from these topics. Yeah.
Okay, I'd love to talk to you about quantum gravity, but before that, I'm really compelled to touch upon the aspect of Schrodinger's equation. Because when you're talking
Mhm.
about quantum mechanics and especially the mathematical side of things, it sort of necessitates for the discussion to briefly just touch upon its significance and the role that Schrodinger equation plays in the understanding or describing quantum mechanics.
Right, right. Um, so yeah, exactly. We can maybe go slightly deeper into how the Schrodinger equation actually comes about. Um, so, if you were to take, let's say, classically, let's ignore quantum mechanics for now. If I were to ask you, how do I get all the information about a particle? what would you say? What are the things that come to mind?
It's velocity, it's position primarily.
Exactly. So,
Mm.
position and velocity. These are two things that completely describe the system, or the position and the momentum, perhaps, which is equivalent. Now, is there a way I can use these two quantities to come up with a single observable or a single quantity that can capture all the information about the system? Because these two are related in a very interesting way. And yeah, that's a question we need to answer. And we can start thinking about this. Well, yeah, there are a lot of other quantities you can construct from velocity. Um, the easiest one may be, yeah, you have momentum, but what can you do beyond that? Maybe an energy, right? Um, the kinetic energy that the particle has, which is dependent on its momentum or velocity. All right. And on the position side, now is the position, um, what does the position tell you? Because if all positions were equivalent, then there wouldn't be any information that you're deriving from it. So naturally, there is a certain discrepancy when you consider different positions. So, what is the difference? And the difference is from the potential energy at each point in space. Um, and this may come in different forms. For gravitation, it's just the height, right? The So it corresponds to the force field you're in. Um, so yeah, you can get a potential term. Now, if I combine my potential and kinetic energies, I get the total energy in the system, which we refer to as the Hamiltonian. And essentially, um, all the information that you need about the particle in terms of how it's going to evolve over time must also be contained within these position and momentum variables, or your energy variable, which is your Hamiltonian. And that's how you act upon this vector, this initial vector that has information about your system, called the wave function, with your Hamiltonian to see how it evolves over time, which gives you the I h bar d over dt of your um, wave function. D over dt is how it changes over time. Now, this wave function could correspond to a lot of different things. It can refer to just an electron, or you can combine the wave functions of electrons and protons, and you can start coming up with wave functions of atoms. Or you can start combining wave functions of different atoms, and you can come up with wave functions of molecules. Or if you want to be really, really adventurous, and if you have a lot of time on your hands, you can start constructing a wave function of you or me. And you can keep going by adding them as linear combinations. Um, and this should also follow Schrodinger's equations. So technically, we are following Schrodinger's equations as well. But the effects, the quantum mechanical effects, are sort of averaged out. That's why we don't randomly pop up and yeah, vanish out of different places in space-time. Yeah. I hope that gives you some sort of or the viewers some sort of an idea about how Schrodinger equation works. Yeah.
Brilliant explanation. Firstly, right. Also, as a side tangent to that, but not too far away from it, how does the entire concept of the quantum state space, the Hilbert space that we have been talking about, how does it inform the idea of superposition? People know what superposition is in a more definitive sense, but when you look at it from a mathematical perspective, how does these subtleties, so to speak, they apply to an infinite dimensional space?
Right. Awesome. So, first of all, your uh, yeah, the space of any operator or any observable isn't always necessarily infinite. So we can maybe start out from the finite case. Um, so just like your Hamiltonian, which I said was a matrix on in this acting on this Hilbert space, um, you can construct other operators like let's say if a particle has a spin or um, yeah, other quantities like this. Uh, you can find a corresponding operator to these things. But let's start out with the Hamiltonian itself. Um, so since it is a matrix, um, it's maybe undergrad physics or even math. You would see this where primarily math, I guess, linear algebra, where you can actually um, sort of you can find these things called eigenvalues or eigenvectors of your matrices. Now, what are these quantities? They're eigenvectors of a particular matrix are vectors that don't change even after you act on them. Don't change in the sense they don't change direction, but they will only be scaled. And the amount to which they're scaled is your eigenvalue, right? So for the Hamiltonian, it would be the scaling of the wave function would correspond to the energy it has, right? And if you're working in, let's say, some three-dimensional space or something, maybe you have a Hamiltonian uh, that's a 3 by 3 matrix or whatever. Of course, there are other factors to the dimensionality of your Hamiltonian, but you would expect to come up with three eigenvalues and eigenvectors for your matrix. And these correspond to the base states or the component states that make up your energies of your wave function. Um, now, your wave function might contain um, a mix of all these three states, right? A linear combination of these states. You can express energies as such. Um, but now, when you actually measure stuff, this is one of the key things about quantum mechanics that we're in some ways still trying to answer. Measurement, what it does to a system. But mathematically, we know that when a measurement is made, what it does is it brings the system down to one of these eigenvector states or one of these base states. This is the idea of superposition. That is, before measurement, it's in a mixed probability state between these three component states. And when you measure it, it collapses down to one state, which is the Copenhagen interpretation. But yeah, when is the measurement exactly made? That's something that we're still trying to understand, and that gets into the foundations of quantum mechanics, and we're still unsure about it. Something so fundamental, but the math seems to work, and that's why we trust it. Yeah, and similarly, you can find operators for position, but for position, you actually have infinitely many. Even if you take the particle to just be on a line, there are infinitely many points, and that leads to an operator with infinitely many basis states, and that's where you get the infinite dimensional Hilbert space for the position of a wave function, where it lands the particle once you collapse it. So yeah, that's the mechanism, and that's where superposition actually comes into play. Yeah,
You said that your research, your area of research and your focus area is lies with quantum gravity. Talk about
yeah,
that a little, maybe. Why is the matter of unifying quantum mechanics and general relativity at large is such a tedious task? And secondly, yes, the mathematical and in general interpretation of quantum gravity.
right. So we stopped at quantum field theory, which sort of is a relatively nice synthesis, haha, relatively, between special relativity and quantum mechanics, where you're also considering um, things like causality. That is, you can't have events that interact with each other beyond the speed of light. Uh, that's where you have stuff that can only affect each other within the time it takes for light to reach there. That defines a certain cone in your space time of events. And you start incorporating these structures into quantum mechanics and define fields. And that's where quantum field theory comes about. This is also called second quantization, because the first quantization was to define these variables like total energy as operators, and then you have all these basis states and everything. But now the second quantization is you make the wave function or whatever dependent on certain points in space and time. So that's where it's second quantized. And there are certain commutation relations between them, but we don't need to really go into that right now. Okay, cool. So you can start quantizing even the force carriers. You can quantize electromagnetism. And quantizing actually refers to our intuition of actually quantifying things. And quantizing the electromagnetic field gives you photons. Quantizing the weak fields gives you other force carriers, namely W and the Z bosons. And for the strong force, which is still work under progress in some ways, gives you gluons. Now, when you try to do the same thing for gravity and get gravitons out, what ends up happening is there are certain integrals associated with quantum field theories that give you infinities. But if there were really infinities, we shouldn't be having a smooth spacetime like we do right now. So this is just one of the sources of why we really can't quantize gravity with the tools that existed before. In order to solve this, many ideas have been proposed. String theory being one of them, where you don't consider your fundamental particles to be point particles, but you consider them to be strings vibrating at different harmonics to give you different particles. Now, why would you even consider doing that in the first place? This was because in the 1970s, people observed stuff that happens in the nucleus, specifically how the nucleons and the gluons, they scatter off of each other, which resulted in these formulas called Veneziano amplitudes. Now, an amplitude is the probability of a certain scattering process to occur. Now, these equations called the Veneziano amplitudes looked very much like strings scattering off of each other rather than just point particles. And this is what led to the birth of string theory. People were like, maybe this is the approach we need to take for all particles. Now, when it comes to string theory, there are a lot of assumptions that have been made. But under these certain very, very constraining assumptions, in these very special cases, string theory has been solved, and it does seem to unify general relativity. Like the equations, Einstein's equations pop out of these constructions, and they are a quantum field theory to begin with. So that's where string theory lies. There are alternate approaches like loop quantum gravity, which tries to calculate something called gauge invariance in your space-time and so on. So yeah, there are a lot of other complicated approaches. But yeah, these are the kind of things I think about, if that makes sense. Yeah.
As somebody who studies this on a daily basis and is trying to figure out how it all fits in the grand scheme of things, what does your day to day work flow looks like?
Right. Um, so I myself am, even though I call myself a physicist, I'm more of a mathematician than a physicist, on a day-to-day basis at least. It involves a bunch of math, essentially, with some coding work, I guess, which would be primarily on this tool called Mathematica, um, uh, which I primarily use to solve integrals and do a bunch of other stuff. But yeah, it's very proof-based math that I'm involved in that helps me understand physical quantities from a, a more mathematical perspective. For example, the kind of math that I do is more topology, combinatorics, on the discrete side of things, symplectic geometry, and all of these areas are involved. But yeah, turns out a lot of information can be derived about physical systems using these this math. Now, what's the point of making all these things abstract? Like, what am I trying to do here? One can view the abstraction of all these physical concepts as using tools to, at the end of the day, solve some and try to understand some differential equations, um, and some algebraic equations. That's the foundation of this. But the way you understand these is through abstraction that reveals certain deep relations and hidden in them that may not be apparent to start off with. Yeah.
What do you think, or how much do you think is the optimum amount of understanding that one must harbor or develop for mathematics to understand or be able to comprehend quantum mechanics and physics at a l- at a deeper level?
Um, I guess to understand uh, the intuition behind quantum mechanics, I think that's what you're getting at. Um, the same kind of probably not, but a similar kind of intuition that the founders of these subjects had, like Heisenberg and Schrodinger. Um, the kind of math that you would need is you need to know how to deal with vectors. So that's where linear algebra would come into play, like basic linear algebra, and if to know how to find eigenvalues and eigenvectors. So if you take a typical course, you go through that and get up to that point. That should be good. Um, some basic calculus, enough to solve some simple differential equations. Maybe even some partial differential equations may help. Um, so yeah, with these two mathematical, I mean, at least subjects on the math side, you will be able to understand quantum mechanics or get at the heart of it. Yeah.
Hmm. You said that you consider yourself more a
Mhm.
mathematician than a typical physicist.
Right.
Is it something inherent, or is that something that you have developed over time?
Um, so my own story, I guess we can go into it. So I did my schooling in Bangalore. Yeah. And ever since I was 10 years old, I wanted to do physics. Yeah, I don't know what drew me to the subjects. It's probably what draws a lot of kids into the subject, which is the fascination with the microcosm, atoms, and so on. Yeah, and then as I grew older, I started even back when I was in high school. I wanted to get ahead of my peers at school, so I tried to delve into things on my own. And I realized even to start off with classical mechanics. So the pillars of modern physics are classical mechanics, electrodynamics, statistical mechanics, quantum mechanics, general relativity, and quantum field theory. If you have this, you can go into quantum gravity. So um, I read a book called The Elegant Universe by Brian Greene, which talks about string theory. And that's a book that really inspired me. So I wanted to go into all of this, and I realized even to start off with classical mechanics, I would need a good background in trigonometry and calculus. So that's where it started. But as I was working on it, I took maybe a couple of months to finish, maybe 3 months actually, to finish trigonometry and the entirety of calculus. Um, that led me to believe that I loved math a whole lot more than I'd realized. So I started working on this field called axiomatic set theory, which is just pure logic, nothing to do with physics. And from there, I went into a little bit of topology, differential geometry, symplectic geometry, and then I realized that I could keep on going. It's just poetry at the end of the day. But it lacked the spirit of physics, which I discovered that I was deeply passionate about as well. So I came back to physics with a more mathematical perspective. So that's when I went through classical mechanics, electrodynamics, general relativity, and quantum mechanics. This was all before I had finished 12th grade. Um, so um, this is when I started realizing that I would like to sit at the interface between being a physicist and mathematician. Um, you do run the risk of not being good at either, but that was a risk I was willing to take, and I'm happy with the work that I do, bringing these fields closer together. Yeah.
Umpteen times, people get this notion that pure mathematics more often than not lies on the idea of convenient abstractions in the stead of imitating or explaining the underlying physical truths. What would your
Hmm.
opinion on it be? Because I think that you will be able to better cater to justify how mathematics actually is able to help you comprehend at first, but then subsequently be able to justify and define the physical reality around you.
Right. Um, I actually don't know if I'll be very helpful catering to that, but I'll do my best. The reason being, it's it's still at a very deep level a very mystical thing that um, yeah, these abstractions always seem to correspond to physics of things. By physics, I mean the mechanisms of the universe at different scales or in different levels of emergence. Um, but at the same time, the physics that we come up with also seem to inform our abstraction again. And there's a feedback loop here. So it's not just that we start off with, at some point, um, from physics and then just take it on a tour of abstraction without ever making contact again back into reality. That happens very rarely, even though the intention is to precisely go away from reality. Um, because that, as a mathematician, that's what we'd like to do. We'd like to reduce things to a few axioms or principles and see the interplay of those ideal principles without any connection to anything else. We want to precisely see justice, and some deeper structures arise from this. Now, these deeper structures, more often than not, end up corresponding to something that we see physically and ties back into reality. Um, and quoting the article of Eugene Wigner, this is the unreasonable effectiveness of mathematics. We don't know why it works, but it works. Um, there is also some, from what I perceive, because of language barriers even between these fields. One might view them as very homogeneous. To the layperson, these fields are very close than what other fields are to each other, right? But even though they're so close, there exists a language barrier between these fields, precisely because of the way that physicists and mathematicians like to think about things, which is what I just described to you. And sometimes this is to the detriment of the field. And this might be the strongest justification as to why um, abstraction is not necessarily a bad thing. Uh, this physicist by the name of Freeman Dyson, you may have heard of him. He has an article. I forget the name of the article, but it talks about how if mathematicians had looked at Maxwell's equations right when they were discovered, they would have been 100 years faster to discovering structures like Lie algebras and Lie groups, which form, again, a vital part of physics, which is in terms of gauge theories and symmetries. This is the study of symmetries in physics, right? So you can see how they deeply connect each other, even though Lie groups are a very, very abstract concept. But they seem to explain our universe with our current level of understanding, at least. Yeah.
Do you think that mathematicians are able to think, be non-conformative, and think out of the traditional ideas that are accepted currently? Like, let's take the idea of multiverse or the many worlds interpretation. What is
Mm-hmm.
the mathematical foundation of it, if there's any, and how does this interpretation resolve some of the aspects? And the underlying question here is, are mathematicians more bold and bodacious to try out different things and venture out and just run these abstractions that we talked about just right now?
Um, yeah. So there are a couple of components to this answer. I'll start out with the last thing that you mentioned. Are mathematicians bold? So the question of being or not being bold comes when they have a certain adversary or a certain obstacle that they need to overcome in the first place in order to scale it, in order to think outside the box, etc. But mathematicians don't have any adversary or obstacles to start out with. That is because, yeah, they don't confirm in the sense that they don't have to um, abide by any other physical constraints in their thought processes. They don't have to take that into consideration. That naturally gives them more freedom, and that helps us in the end as physicists. That's correct. Um, right, that was one. Could you repeat your question again? There was another part to this.
The mathematical foundations of the conception of multiverse and the many worlds interpretation.
Exactly. Right, right. So, regarding that, that was actually not the invention of a mathematician, but rather a physicist. So, remember how I told you that you when you measure something that it collapses down to one of the states. Now, let's say this doesn't describe the collapsing of the state, but rather the trajectory that our entire universe takes, the micro trajectory. Why I call it micro trajectory? Let's say that there was another universe itself, that in which when you measured some particular thing, instead of collapsing down to state A, it collapses down to state B. So it's not describing the particle, but rather the universe itself. And now there are successive measurements like this. For example, when a photon interacts with an electron as part of the photoelectric effect, that can be considered as a measurement per se, even though there's no human observer. Um, and maybe that results in the collapse to one of the states and in our universe and another state in another universe. And it's just uh, a happy thought experiment, I guess, what the multiverse theory is. Um, then in string theory, we also have math that describes the evolution of entire universes, the space-time and stuff like that, um, which can accommodate for other universes. But as far as concrete evidence and proof, as that is how we progress in the sciences, we don't have any. So it's a happy idea that we have that has given rise to a lot of fiction, and I'm happy that it has. But in terms of the actual physics content of it, they're just ideas at this point. We don't know if there are or there aren't, and we can always come up with math that can fit any idea that we want to be incorporated into physics. That's something that is maybe a downside to abstraction.
What about the matter of consciousness? How much do we know
Mm-hmm.
about it from the perspective of physics, and what are the are we is there any mathematical basis to it?
Wow, that's a very, very deep question. Now, um, the I would say the closest mathematical basis for any semblance of consciousness comes from the mathematics in the 1960s that was invented for neural networks that are used presently right now. So believe it or not, the first conceptions of a neural network was done way back in the 1960s. Um, Now, why I say semblance of consciousness, because honestly, we don't have a good idea of what it is right now. But if you see your large language models, they clearly can mimic something like consciousness, but we're not sure. And well, we're sure that it's not conscious, but yeah, what is consciousness at the end of the day? No, we have no idea. There have been a couple of proposals, and a lot of very good people work on this. As a physicist, uh, Roger Penrose has certain conceptions of it that involve um, these things called microtubules inside your brain, and there are certain. He claims that there are certain quantum mechanical processes that are associated with it, um, which may be true because at the end of the day, there are fundamentally quantum mechanical processes occurring in your body, even with the transmission of, even with the interaction of neurotransmitters and receptors. It can be modeled as a quantum mechanical system, a very complex one. Just to model one receptor and neurotransmitter molecule interaction. Now imagine billions of these. It's very hard for us to quantify it. People do take certain liberties in popular science, claiming consciousness having quantum mechanical origins and so on. They may be right, they may not. But with the current state of things, we actually have no idea. That needs to come about as a result of the intersection of fields such as neuroscience, physics, which is growing right now. But yeah, we actually don't know the short answer of it. Yeah.
If you were able to, or if you were to put a timeline about the next up and coming milestones and breakthroughs in theoretical and mathematical physics, what do you think would they be, and what sort of impact would they have on the theoretical advancement but also practical reality and technology?
Right. So if, I mean, it would be a dream of mine to uh, there are a lot of open questions in physics right now that would help us move towards quantum gravity. But my personal feeling is there needs to be a certain paradigm shift. Because even quantum field theory, right, even though it works so well, it's actually a divergent theory at the end of the day. And we don't know why it works so well, because it doesn't converge in the perturbative expansion. And this is a central problem that I personally would like to understand, because this seems to result in a lot of the divergences that we see. Another thing is we need to understand renormalization, which is the process of it's not a very mathematical process. It's what physicists came up with that seems to work, that helps us understand quantum field theories at different scales by adjusting certain parameters as we keep scaling. So that's essentially how renormalization works. But it doesn't have a very rigorous mathematical foundation. If you ask mathematicians whether quantum electrodynamics, that is quantum field theory applied to electrons and photons, exists, they would say it doesn't mathematically exist. That's these are things that we need to clarify for ourselves before we even start to attack the mammoth task of quantum gravity. It's the fundamental things that we still don't really understand. And I believe it will come about as a paradigm shift where the math that we use, or even the theories that we use, would be a leap beyond what we have presently. That's what happened to our understanding of gravity with general relativity. It was a fundamental leap in how force works, not as something that acts at a distance, but rather through the curving of space-time itself. That's the kind of leap that I expect to happen in the field of quantum gravity, and that would reshape our understanding of quantum mechanics, general relativity, and everything that comes after that. The primary application of this would be we would finally know what happens inside black holes. Because black holes are these very curious examples that are perfect for quantum gravity, where the the space-time intervals or the distances that you're dealing with or the scales you're dealing with are very tiny, but the masses you're dealing with are very large. So you have proper effects of gravity and quantum mechanics coming together. Um, so that would help us understand how singularities come about, which would also probably explain where our universe came from or what existed before our universe. Um, Now, you might ask, well, this is not really, you might say, this is not really application because I don't get to use it. But it does make a difference to know where all of this essentially came from at a very, very deep level. And that goes beyond any claim for practical importance, in my opinion. Um, but yeah, those are two places. And of course, the math that would come out of this, as it has done in the past, is directly applicable to fields like condensed matter physics, superconductivity, topological insulators, as I mentioned. These were all math that was repurposed, so to say. So yeah, that is what I would hope to see. Yeah.
Two different things that I think run parallel to each other. First of all, what drew you and what still draws you to this entire field domain of quantum gravity specifically? Secondly, how would you advise the young students or the aspiring researchers to engage with the theoretical, mathematical, and experimental aspects of quantum mechanics at large?
Right. Um, what drew me personally was more aesthetic. Um, yeah, um, it's very deeply satisfying to um, be in pursuit of something so deep, at least materially speaking. I would claim that it's the deepest materialistic uh, reality that or material reality that can be discovered or understood. Um, so yeah, that's the bottom line. Is it's just that, and um, I don't know if you've heard of the concept of flow or the flow state by Mihai Csikszentmihalyi. But that's essentially the state I feel myself get into when I work on these topics. Um, and that's a natural sign to uh, keep continuing to work on this area. And that also ties into the second question to aspiring physicists or scientists or anything that you want to do. See what gets you into that flow state where even the personal ego starts disappearing and it's only the work in front of you and everything else disappears. That's what you should aim for. Now, there are certain practical things that you need to consider when you're trying to go into either experimental or theoretical physics. I have a very contrarian view to, I guess, either the theorists or the experimentalists that go, and a lot of phenomenologists also have this view that even though you work in either of the fields, you can't completely give up the other field that you're not involved in. Theory can go so far, but it's the experimental work that should be the sure test of your theory. It's your theory is not complete unless you have experimental backing, and that's the harsh truth. Yeah, we are far behind in technology. Yeah, we are, and until then, we have nothing. For the experimentalists, I think they are more sympathetic towards the theorists. But yeah, be on the lookout for the theories that are out there and help us come up with ideas to actually test out our theories or yeah discover implications that can be seen easily. But yeah, I wouldn't. What I would suggest people do if they are aspiring to get into physics is to not have an aversion to either of the fields uh, and be very democratic when it comes to uh, going ahead with their studies. Yeah.
A continuation to this, what would you suggest as a very tangible and practical routine of sorts that people can imbibe in their day to day lives to sort of enhance and uplift their overall workflow of engaging in research and development?
Um, it's I guess again, since I'm coding a lot of books, there is this book called Deep Work by Cal Newport, and yeah, you can spend time learning more about how you work, why you work, and so on, which is all very necessary and has to keep happening in the background. But the primary thing is to practice deep work. Work where even mentally you're not distracted by anything else. Pick up any topic that you like and just immerse yourself in it. What does that immersion entail? It entails you not shifting your focus even mentally. Like when you're working through a problem, you shouldn't be thinking about what you have to do next after you finish the problem, or any tasks that you've kept aside, or family, or nothing of that sort. It's complete immersion into what you're doing at that moment. And the benefits of it won't be immediately evident, uh, but over time, you will see the accumulation of the value uh, you've added to your work. And it essentially boils down to adding value. And through work, deep work is one of the primary ways and the most effective ways you can add value. Um, yeah.
It's very apparent that you read quite significantly, and it again compels me to ask you this: how significant is reading for, in general, personal enhancement? And yes, like anything and everything that you would like to suggest the this carer of young audience regarding
Yeah.
reading and its significance.
Yeah. Um, the interesting thing is, growing up, I never read. Uh, yeah, I was more of a go play outdoors kind of a kid. Um, so initially, the what drew me to read stuff was if I could get any value out of it. So as a result, I was never into fiction growing up. It was only nonfiction because if I was spending time reading, I had to get something out of it, which isn't the best way to start off your reading, your interest in reading. But the even the act of reading, I would say later on, as I discovered, is an act of meditation, as is all work that I do. And this is where the concept of deep work first came to me before I found the book, because people naturally do this, and um, it's something that cannot be articulated, but you definitely feel um, that you essentially end up transforming as a person. You're in what exact ways you might ask, and how much effect it would have, you might ask, but it's honestly very difficult to quantify. Um, but one way of directly seeing this is that you come into contact with different perspectives, and that's the most important thing. Um, Different processes of thought uh, that the authors have. You get to peer into their minds. Um, and we, being humans, uh, benefit from this synergy, this interaction of entire consciousnesses coming together and influencing each other. So at a certain point, once you start reading more books or talking to more people, you start becoming a focal point of these different influences. And that can essentially help you influence other people as well, um, in the direction of deeper inquiry, which is something that's inevitable once you become this focal point. I know it may seem very abstract and hard to understand, but once you start reading, employing deep work, these things become a living truth, not something that you'll have to really intellectualize about. And you should not intellectualize these things. It's just my experience. And once you start reading and practicing deep work, practicing meditation in everything that you do, you'll start experiencing you'll start having your own experiences and you'll see for yourself. Yeah.
I I agree. Oftentimes, people also have this misconception that reading particularly pertains to the entire exercise of holding a book and sitting at a place and going complete full throttle for another hour just going through the pages. I mean, reading an
Yeah.
article that of value of your interest, it equally
Yeah.
aligns to the habit of reading. And
Yeah. Yeah.
that is actually how you develop this entire meditative routine as you spoke about. Because
Right.
again, it's it's
Exactly.
it's it's very significant. Meditation doesn't always have to be you sitting down, closing your eyes, and just that's a type of meditation. And you very
Yeah.
wonderfully stated that all the work that you do, that is part of the meditative process, the meditative practice that you exercise.
Yeah. Exactly.
So
Yeah.
I think that's again a very significant tidbit that people really need to realize and start incorporating in their lives, especially the ones who are younger right now. You know, the
Yeah.
school kids,
Yeah.
high school kids, the people who are just went into college and they're doing their master's, PhD, whatever. I mean, everybody,
Yeah.
but significantly the people who are relatively at the earlier stage of their careers and life in general.
Right, exactly, and ever more so because there we have a problem of well, mostly have a problem of abundance as opposed to a problem of poverty, which also exists. But yeah, and what abundance does is it overstimulates and leads to a lot of disorder. But you need to structure it through this. Yeah, exactly.
As much as I'd like to continue the entire conversation, and trust me, there are a plethora of tangents that I could take right now, because I came into this discussion with the preemptive thought that I'd be very strictly sticking to the theoretical and mathematical aspects of the conversation. But
Yeah,
as the conversation, our talk progressed, there are sometimes people, and you mentioned this a little somewhere in the conversation about having this multifaceted nature, right? And I think reading
right,
again develops a very multi-dimensional personality, and we
right,
did went
exactly.
on to talk about all those aspects. But
Yeah.
coming to concluding this episode in particular, there's this
Mm-hmm.
final segment that we do on the show.
Mm-hmm.
What is your word for humanity?
What is my word for humanity? Um, that's very interesting. Uh, so I would say it's transcend in terms of paradigms, but yeah, transcend probably. Yeah.
Okay, I am
Oh,
again compelled
uh,
for you to elaborate upon that a little bit.
elaborate. Yeah, yeah, yeah. Of course. So often the problem with we have while we go ahead with things evolve in our own personal ways or as a society, etc. We get stuck with the current paradigms that we have. That is, the issues that the problems that we have are mostly likely associated to the current circumstances, the current paradigm, the current equations that are around you. But a general principle in life is um, these paradigms keep on changing. And the problems of today most often aren't the problems of tomorrow. They usually take different forms, and the problems are always going to persist. And this leads people to be very nihilistic, and yeah, they get bogged down by everything that exists today, and there is lack of optimism and uh, overall motivation to for the betterment of everyone, and you get into a survival mindset instead of living your life. Um, but once one is aware that the problems that exist today pertain to the paradigm that you exist in, and this keeps on changing, um, and you detach yourself from the present circumstance and can actually attain a quietude that lets you observe things as they progress. That's when you start discovering the deeper principles of life. And once this happens, you can greatly affect the shape the entirety of society takes, or starting from just you to everyone around you to larger and larger scales. And that's what I meant by transcend the paradigm that you're in. Yeah, become the observer. Yeah.
Wonderful, wonderful, truly, truly wonderful. Uh, Mr. Rahul K. Balaji, thank you so very much for being on the show. It
Mhm.
was really a very Not only delightful but profound conversation.
Yeah, yeah. Likewise. It was really nice talking to you, and I love the fact that you're doing this
Hmm.
because this mode of sharing information, podcasts,
Hmm.
have um, become very ubiquitous now.
Hmm. Hmm.
They are present everywhere, and to use that as a tool to lift people through this by exposing them to the stuff that's out there, that's really fascinating. It's great work that you're doing, and I wish you all the very best for all the future
Thank
episodes.
you.
And
Thank you
yeah,
so much.